Okay. In our last lecture, I explained about the basic idea of the what's the importance of the STT name and what's the mechanism of spin transfer torque for the current-driven monetization switching. And the important thing is how much current we need to switch the field layer. So in order to get critical current density, I want to solve the energy equation with the first order linear approximation. To do that, first let me introduce the susceptibility concept. And as we already mentioned in our previous class, we assumed we want to find the susceptibility as a function of the external magnetic field. And that susceptibility determines the motion of a small magnetization, which one is, we assume, the ground state of magnetization is along the g-axis. And with the small perturbation, there is some motion of the magnetization. The small portion of the magnetization will be added up to the original one. Okay, in that idea, first we introduce the effective field, which one is generated from the various energy. And then magnetic moment is aligned to the ground state direction. We assume the G. And by applying the harmonic external magnetic field, the harmonic means the time variation is described by exponential I omega t. And this phase term can be set up the field in any kind of polarization. And the goal of state study is finding this susceptibility. And it can be achieved by solving the coupled first order differential equation. Actually, there is two coupled first order differential equation of the mx and my. So we can represent that kind of first order differential equation in this matrix form. But when we substitute the mx or my to other equation, we can obtain second order differential equation. And this second order differential equation is actually quite similar to the first harmonic oscillator solutions. So I want to recall that kind of simple mathematics to remind you. Okay, so this is the one example. This is a numerical solution, and let's assume the magnetization is pointing to g-axis here. And let's apply the external magnetic field to the minus direction. And we assume the damping constant is 0.02. So this is the result. We starting the +1 of the mg. I'm sorry, now in this calculation I use the x. And they are starting the +1, and eventually they go to the -1. That means they are switched to the external magnetic field. And as you see here, there is some kind of oscillation. And also mx and my is from starting to 0, and there's some strong oscillation and damping out. It's similar to the mg. But please remember that the magnitude is different. And in our right panel, we use the different damping constant, which is much smaller than 0.02. We using the 0.05. And the overall physics is quite similar, but the difference is this damping time. We are using the same time scale here, but this damping time is different because we are using the small damping value. So that means if we have a large damping, actually the starting point of this time is quite similar. So this time doesn't matter of the, it's not sensitive to the damping constant. But when they are started to switching, this decay time or the ending of the switching time will be depend on the alpha. Please keep in mind, in a strong alpha model, they didn't know about this kind of oscillation. In a strong alpha model, they just stable here, but they are just switching to here. And they didn't describe this kind of intermediate state in a strong alpha model. So error education is more accurate and they can describe more. But unfortunately, that solving the error education is usually not easy. So is it clear for you the difference of the strong alpha model and the error educations? Okay, so let me recall the damped harmonic oscillator or forced harmonic oscillator. Actually, I already mentioned this things one more time when we talking about it. So we do the damping and with the external force with the driving frequency omega, then the solution can be obtained in this form. The displacement as a function of time will be determined the magnitude of the applied force and the same frequency and with a little bit different phase. And the magnitude of the displacement will determine this part. Okay, so when we apply the omega to the omega zero is resonance frequency of the system here, and here. And omega is omega zero. They can be maximized because they go to zero. So that's called the resonance field, resonance frequency. So at the resonance, the energy from the driving force can be absorbed the spring more effectively, most effectively. Okay, and in this line width will be determined by related to the damping constant gamma. So please try to find this solution by yourself. Yeah, from here to here. That's a good exercise. And also, you may think about the RLC circuit. If we have a resistance, inductor, and capacitor in a series, when we apply the external time-varying volt, external driving voltage in this form, and we can measure the current as a function of time. So in this case, this I0 has a deceleration. And the phase difference will determine the omega L minus 1 omega C divided by resistance R. So in this circuit, actually, the equation is the sorry, this is plus. This is the voltage drop because of the inductor, and the voltage drop because of the resistance, and voltage drop across the capacitance. So all this voltage drop should be same to the applied voltage. So this differential equation, if you take the one more time derivative, we can obtain the this one. And this second order differential equation actually is mathematically exactly same to this one. So this first harmonic oscillator and the RLC circuit is physically equivalent. So when you solve this current, this is quite similar to the displacement in a first harmonic oscillator. So we obtained this kind of expression with the I0 as this form. So that means when they satisfy this condition, or the omega is satisfy this relation, then we have a resonance, because this term is going to 0. So at the resonance, we have a more simple form, and in that case, the current can be maximized. So the resonance frequency will be given by this form. And as you see here, even though we have a same inductor and the capacitor, the magnitude of the current at the resonance condition is changed by the resistance value, because we have this relation. Okay. So let's back to the magnetization again, magnetic system. So we assume the ground state magnetic moment with the small disturbance, and let's assume the ground state is g-axis with the small magnetic moment. So it is natural that the solution of this problem can be set of this form. So this is something like we assumed this form of the solution of the RLC circuit. And then you can find the I0 and the phase difference phi from the given circuit parameters. Okay. So that's the call tail solution. And here, M0x and M0y represent the x and y magnitude of the x and y component. And this is the oscillating part, time varying part, with the phase difference. Okay. And here, this cartoon represents the situation. If we have some magnetic object with the elliptical shape, and the magnetic moment direction is, let's say, this axis, the g-axis, then we apply small disturbance, small field to perpendicular direction. Okay. So let's try to find the susceptibility. Okay. So after finding this susceptibility of the analytic solution, we can find the resonance condition, and also we can find some unstability condition. So this unstability condition is very important to understand the switching. Okay, so if we add up this spin transfer torque term, the problem is a little bit more complex, but let's do it. So as we already explained, we insert the magnetic moment in this energy equation in this form, with the assumption of this trial solution. Here, the difference from the previous one is we assumed the exponential kt instead of the external I omega t. So in this expression, omega is a real number. So they can give us only harmonic oscillation. But if we assume the expression of the exponential kt, here the k value can be complex number. So that means this is this form. Let's assume the k is the complex here. Then I alpha t give a oscillation, while here we have minus sign because of 2 I. This term gives us exponential decay or exponential growth, depends on the sign of beta. So if the beta is positive, then the solution gives us decay or damping. That means if we have a ground state in this direction with the small oscillation, there is some kind of the vibration of the momentum moment. But with the finite damping, they're gonna back to the ground state. And what happens if beta is negative? This term gives us exponential growth. So if we have a such situation here, the small m is no longer small because we assume the small m is much larger, smaller than ms. But with this condition, this term is no longer small. That means our assumption is no more valid. So something going wrong. So that means that kind of solution is no longer stable. So the system can be unstable. So what's that mean? That means our assumption means the momentum moment is aligned to the z-axis. It's no longer correct. It's not correct anymore. So we need another solution. So that means we have a switching. So this condition gives us unstable, and that implies switching. So that means we have to find this condition. So please keep in mind that kind of idea. And we assume the H effective field. We ignored some other factors, or we may involve any kind of energies to determine the direction of the effective field. And then we think about the Dirac field. The Dirac field means, as we already said, the Dirac field is determined by this form. Here, n is the dimensional factor tensor, or it can be matrix, but generally they have a diagonal form when they align to the principal axis of the ellipsoid. So we have the g component of ms, this form, and x, y component, and we have a Dirac field of the Dirac coefficient of the ng, nx, and y. Okay. So please remember that in a film, in thin films, if we assume the x direction is here, and g is this direction, and y maybe in this direction. So in this case, the ng gives us 1, while this is almost 0. Okay, so please that things. If you cannot remember the Dirac field or dimension coefficient, please take a look at the previous lecture. That's the important concept. Okay, so let's think about each term. First, the time derivative of the momentum moment. If you take in the time derivative to here, this term will be disappeared because we assume they are stable, they are constant. We only think about this term. And as you see here, we got a k in front of the mt. So the dt can be changed to the multiplication of k. Okay, in this form. And then let's think about the precession term. Yeah, I'm going to explain term by term. Here, the M is, this is M. And H effective is here. We have this form. And then let's do the cross product. So simply, we have three terms, x, y, g, and x, y, g. So we have actually uh, 9 terms, and the parallel term will be disappeared. So we're going to have 6 terms. But here, we take the linear approximation. We already assume this m0 term is small enough. So let's ignore the m0 x square or m0 y square or m0 x, m0 y. That's the second order. So multiplication of this term, actually multiplication of this will be 0 because they are 0. And also this term with this term give us the second order of m0x, m0y. So we're gonna ignore them. In that kind of linear approximation, the surviving part is here. Okay, multiplication of this term and this term will be disappeared because they are same g. So with this term, only surviving term is here, this form. And with this term, only this term will be survive. And by the time, because of the vector product, we have a change of x, and y. And there is some common point, so we can collect them. So you have to do it by yourself to understand more details. So please remember that here, we don't have g component. We have only x and y component. And here also we have x and y component. Okay, during my explanation, if you have any missing point, please let me know. Okay, so let's think about the damping term. Let's do it again. M cross here, dm dt, we already obtained here. And then this term is here. So multiplication of this term and this term will be disappeared because of the second order. So we assume the linear approximation. The remaining part is the cross product of mg and this term. And the ms will be dropped with this term. And then the x, y can be changed to y and minus x. So we have this result. So we still have a x and y component only. So, and now think about this STT term. So we repeat this kind of cross product again, and we can obtain this form. So we have only xy component. Is it okay? So let's collect all this term. So this is about the MDT, and this is M cross H, and this is the damping, and this is the STT, and this is also the M cross H term. Anyway, so we can write down this equation to this matrix form. Actually, we rewrite this term for each one. This is a mixing of the x and y, x. Okay, so we can rewrite this equation to this matrix form. So this is the DMDT term, and this is the M cross H term, and this is the damping term. This is STT term. And please remember that here, this is the off-diagonal element. So this off-diagonal element gives us the mixing of the mx and my. And this diagonal term gives us just a simple differential equation. So yeah, it looks complicated, but we can do it more because it's just a simple matrix operation. Okay, then we can rearrange the matrix in this simple form. So when we have some matrix with the x vector and they give a 0, then what is the condition to obtain the solution? Yeah, I believe everybody already familiar with the linear algebra. So in this case, if we have an inverse matrix of this matrix, then we can multiply the inverse matrix in both sides. Then we got a 0 here, because so they give us only trivial solution. So in order to obtain the non-trivial solution, the determinant of this matrix must be 0. Okay, so let's find the determinant of this matrix. So multiplication of these two terms and minus multiplication of these two terms here. And we have a plus sign because we have a minus here. Okay, and then this is the k-square term. We have a k-square term and k-linear and constant term here. And here, we also have a k-square term. Actually, this is the something like k plus a square plus k plus b, k plus c, something like that. Okay, so this is the quadratic equation for the k. So let's collect the square of the k terms and the linear terms and the constant terms. So this is nothing else but these quadratic equations. Even though the coefficient looks like a little bit complicated, but this is, let's say, a, this is b, this is c. Okay, so what we have to do? Finding the solution of this quadratic equation. Now I believe every student will be happy. You know the solution, right? So let's assume this is very complicated, looks very complicated. So let's introduce new variables. Here the blue one are same and the red one are same. So let's redefine the new variables in this simple form. Here the y here and x is here and other thing is same. And I'm going to explain the physical meaning of this term later. So that equation, that quadratic equation can be written in this form and it's much simpler. Okay. And let's find the root of this quadratic equation. So you know we have this solution. Let's do it. Here, that's the result. This is corresponding to B, actually half B, and this is AC. This term is corresponding to B, minus B. Sorry, minus half B. Okay. Yeah, still is very complicated, but let's assume small alpha. Yeah, alpha is generally small. Then we can ignore the second order term of alpha. And this term can be dropped. So the K is more simple form. From here to here, we also ignored the second order of AJ. Here we have AJ square plus 2 alpha square. Those terms are all dropped. Only the cross term is survived here. So generally that is good enough because we assume the effect of the STT is too small. So now we are getting close. So if we have a no STT, then you can obtain the even simpler form. Okay. And let's introduce new variable. The multiplication of x and y h 0 with the root. Then if we have this form, we call this is the geometrical average. Right? So this is nothing else the geometrical average of these two fields. Actually, this is the form of the field. Okay. And as we already know, if we multiply the gamma with the some field term, we can generate the frequency. So let's define this frequency is omega resonance. Okay. Then this form is even more simpler. Oh, sorry. We didn't assume the STT is 0. Sorry. we have a STT here. But we ignore this term because the AJ is small and alpha is small. So we can say this term is approximately second order. So we can ignore this term. Sorry. And then let's write again. We assumed the time dependent of the multi-moment. This is trial solution of the form, and K vector is here. Okay. Let's assume if there is no STT and no damping, this term will be disappeared. So that means it's a KT is give us exponential plus minus I omega resonance T. What's the meaning? The M magnetic moment has a small oscillation with the magnitude of M0x and M0y. And this resonance field is the geometrical average of these two field terms. And if we assume the N G and Ny is 0 and Nx is 1, so in that case we have this form. Yeah, some student who is working on FMR or BLS, they know what's the meaning of this one. That's the resonance frequency of a given sample with the external magnetic field aligned to the z-axis. So that means the magnetic moment along to the z-axis is rotating with this amplitude. That means the magnetization is vibrate with this resonance frequency. So the physical meaning of this is the this is the actually this is the external field, and this is the DMAC field to the competition between the G and Y axis, and this is also G and X axis. So this is the kind of returning the restoring force to the X and Y direction. So please remember that if you have a harmonic oscillator of the spring constant of K, then the resonance is root K over M. So if you have this is a linear motion, but if you have a two-dimensional harmonic oscillator, then this omega frequency is related to the returning force, the geometrical mean of the two direction of the returning force, something like that. Yeah, so this should be something like that. Anyway, so this result implied us the resonance frequency or oscillation frequency will be mainly determined by the DMAC term with the external term. Okay. Then if we have a damping without STT, we have a yeah, if we ignore this term, we have this finite term. So here, this time-dependent M can be expressed by the resonance term and this term. Here, the tau, 1 over tau, is determined here, and the omega d is sum of these two fields here. We add up two of them. We have this form. Here, let's assume the ng and y is 0 and x is 1. So we have this form. Okay. So we can determine the omega d is the average of these two fields. Sorry, the omega d is the linear average of these two fields, while omega resonance is the geometrical average of these two fields. Okay. And here, just a moment. I missed some sign here. It should be negative. Where I missed the sign? Yeah, it should be. We should have a minus sign somewhere. Oh, I'm sorry. Here we have a B. Sorry about this. We should different sign here. It should be minus. And we're gonna have a the minus sign, and we have a minus sign here. Okay. Is it okay? Do you understand what I mean? Okay. So this should give a damping. That means, yeah, this is the some kind of oscillation. As you see here, it's damped oscillation. And yeah, this is some numerical solution with the STT. Here we have a small current, then we have a damped oscillation, damped motion. But when we increase the current density to be more, they have a amplified. And even we apply the large current, the oscillation is getting larger. So that means here in this term, if AJ is larger than this term, then what happens? They can be positive. So please remember that I said in this form, if we have a beta, the real term is negative or positive, they can be damped one or the oscillation, then they give us some switching. So, yeah, I don't know why I missed the sign again here. Yeah, when K vector is become positive, then we have a instability conditions, and in other words, we have a switching. So let's calculate this one again here, this condition. So AJ should be larger than this form. Here, hx0 plus hy0 give us, the half of them give us h external minus this form. And generally, this is 0, this is 0, this is 1. So anyway, so let's recall the AJ here. Then the condition of the critical switching field, switching current, is given by this form. Or with this and x is 1 case, they turn out to this form. Right? So this is called the switching current density. When we applied larger current density to the switching current density, we can obtain the unstability condition, or we can obtain the switching of the STT. So please remember that here, let's think about this condition again. If we ignore no STT case, we have a unstability condition of this form. In this equation, I'm sorry, this should be negative. And then the alpha will be disappeared. It doesn't matter of alpha in a field switching. So in this case, in this term, we can find external field when they have a same two or that's the switching condition when they have a only Dirac field. So if you have a honest field, if you have a honest field, this is turned to here HK should be please remember that we determined this field when we talking about the strong alpha model. So we have additional HK terms here. Then if we ignore the Dirac field, the switching condition is nothing else but this is 0. So when we apply the external field smaller than the analytic field, smaller than the analysis field, switching occurred. That's the result of the storm Alpha model. So this linear energy equation solution, they can provide the result of the storm Alpha model also. So anyway, let's the switching current density here. So the switching current density of thin film means when they heading to one direction, or if we have an ellipse, we have a EJ this direction because of the shear entropy. So when you're switching to the other direction, we need at least this current density. So that's the for the in-plane magnetic analysis case. Then what happens for the PMA case? PMA case, we have a EGX to the G direction. And we have a 1 for the NG. So we have this form. Because we have a external analysis field in a PMA. Without external analysis field, we cannot achieve the PMA. So without external field, if H external is H external plus HK, but we don't need an external analysis field. So we can rewrite the equation in this form. Or this term can be this is HK minus MX. So this is determined by this new variable K effective. So we can rewrite this form again, or HK effective. So generally, HK effective is much smaller than this one, because without the field, we still have this term. This term can be order of Tesla, while this HK can be shrink down only point something Tesla or 0.0 something Tesla easily. So we can reduce the switching current density a lot for the in-plane, the PMA case. Okay. So why that required switching current density for the IMA is larger than PMA case. This cartoon represents that result. When the magnetic moment aligned to EG axis in plane, in order switching to the other direction, they should switching to from here. This is PMA case. This is IMA case. Sorry. So when we have a magnetic moment in this direction, and switching to here, the trajectory of the magnetic moment should be pointing the perpendicular direction. Which one is they don't like it. So they require large energy or large current density. But in the PMA case, the trajectory involves the in-plane directions. But to overcome this kind of barrier, we need only this term. Okay, that's why we have a smaller current density for the PMA. The DMAC field can help the switching in the PMA, while the DMAC field acts as a barrier for the IMA. So if we make the PMA for the MTJ, we can get a smaller current density, smaller critical current density. So we solve this matrix equations already, and we obtain the value of k for the oscillation case or damped case or switching case. And from this equation, if we insert the obtained solution k to here, we can find the ratio between x and y here. The ratio is given by this form or this form. Here the difference is here. When we insert the condition of k, let's think about the first one right here. It's a little bit busy one, but somehow you can do it. And we can insert this relation, and the ratio is here. In this form. We assume the zero current and the small damping case. So this is actually gamma root hx0 hy0. Please remember that. So gamma can be dropped. And this comparison between the geometrical average of this two equator field, and this is nothing else but hy0. So this is actually the result is plus minus I root hx0 hy0. Sorry. Yeah, that's right. So this is the ratio of these two fields. So that means the magnitude of these two direction oscillation will be determined by this form. Okay. So if we using that relation again, we can obtain this form. Or this form depends on here. I assume we play with this term. If we play with this one, we can obtain this one. So that solution is corresponding to the y or x-axis are perpendicular because we assume the g-axis is the z-axis in these our calculations. So the perpendicular direction can be x or y. It can be x or y. So anyway, that means same situation. So this is a ratio of the external field with the magnetic moment and the external field. So what does that mean? The motion, as I said, if we think about the magnetic moment, is along to the g-axis. This pointing up is g-axis now, and the oscillation, the magnetic moment oscillation, okay. So this is the side view of your samples, and this is the direction of the magnetization. And the external magnetic field, small h, can be x and y component. So this form. So for the simple case, we think about just a small h x. Then what happens? The moment is moving to this direction. But because of the damping, the DMAP field, they are back again. So somehow with this oscillating external magnetic field, there is some oscillation. So this oscillation amplitude will determine this ratio. So this means the oscillation shows some kind of elliptical form. because if this is the side view, the mass moment is initially pointing this direction, they oscillate this kind of elliptical trajectory. But in this case, this direction magnetic amplitude is small compared to this one, because when magnetic moment is moving to this direction, there is no largely restoring force, so they can move largely. But when they wanna move to this direction, they wanna strong restoring force because of the dynamic field, so they cannot make a large movement. Okay. So, but in a PMA case, they give us just one, the different phase. That means if we have a PMA, the magnetic moment direction is here, and this is G-axis, then motion for the XY direction are free. So they are circular, they are symmetric, so they generate the circular motion. Okay. So I hope students can understand the difference of this elliptical form and the circular form. Is it okay? So yeah, let's back to this numerical one. So this numerical result represent our result. When you apply the small current, which is smaller than switching current, they start to oscillate, but eventually they go into the stable condition again. But if you apply large current, then oscillation amplitude is getting larger and larger. And if we have a large enough switching current, we have a amplitude increase by the exponentially. So in a same time scale, the switching can be occurred more easily and faster with a large applied current. Okay, so now we have a final view graph. Compared to the switching by the field and the STT, in a switching by the external magnetic field, we have such kind of binary stable energy point. But if you apply the external field, this part, this direction energy is getting lower and this energy getting higher. We already solved in a strong aperture model. So energy changes, and finally there is some switching. But in a STT, with the external current, the energy barrier is not changed, but the magnetic moment can be excited, something like this. And then if the excitation is getting larger enough, then there is some switching. There's a difference between the field-driven switching and the current-driven switching. Okay, so this is the end of today's lecture. Today, I explained a lot of things about a lot of equations and mathematical expressions. So I hope students can follow it. If you have a problem to understand these equations, please do it by yourself at least once. That's very important procedure. Okay, so it's time for the questions. Please ask me any questions about today's lecture. PMA and IMA is kind of energy minimum without any external disturbance. So actually, it is impossible to change IMA to the PMA or PMA to the IMA by the spin transporter. But there is other technology called voltage-induced anisotropy change. So with apply the voltage in a ferromantle layer, they can alter the electron state at the interface, and as a result, the anisotropic energy can be changed. So in that case, IMA to PMA or PMA to IMA is possible, but that's the totally different mechanism to the STT. Any questions? Do you mean this part? Can you tell me the page number? Oh, you cannot say the page number, sorry. In the numerical solution? This one? Okay, here. Yeah, when we have a external, there is some excitation of the magnetic moment, but there is some damping force. So if your current is not large enough to overcome the damping, they're gonna damping. But in this case, the damping is much slower than natural damping without current. So that means the STT acting like an anti-damping, so they can reduce the damping constant. But in this case, the STT effect is overcome the damping, so they're gonna the energy is getting larger and larger by the oscillation, and even higher current density, the damping effect, the anti-damping effect is getting larger, and there is a more faster unstability can be achieved. So that means the switching can be. Is it clear? Okay, if you have some problem to understand, you may contact me. Victor, Leah, are you guys okay? Good. So such kind of approach, the linear approximation and finding the unstability condition, that can be either many physics. If you think about, if you are working on any kind of dynamics, you can apply such kind of approach. So that's good example. Yeah. I'm gonna upload our slide, the PowerPoint after I correct my mistake. And I'm gonna upload also the homework for this chapter. Okay, if there's no more question, let me close today's lecture here and see you next Monday. Okay? Okay.